Integration by parts is a pro-level BC-only integration technique. So what we want to be able to do is take some antiderivatives using this process called integration by parts. Integration by parts comes from, or it has its origin in the product rule. So let's take a moment, if you will, to review the product rule. So the product rule, I'm taking the derivative of a product. You might remember whenever we first introduced this ages ago, back when we were babies, that we looked at it as twins dating twins. Okay, so I'm going to take the derivative with respect to x of u times v, where u and v are differentiable functions of x. The way that we stated it was that it was the derivative of the first times the second plus the first one times the derivative of the second one. So I just rearranged these two terms here. So again, derivative of the first function times the second one plus the first one times the derivative of the second one. And the reason why I switched the order of these two things is because we usually write this in terms of like the Leibniz notation with the du dx. Okay, so here's just one more time a recap of the product rule. Two differentiable functions, this time f of x and g of x. We're taking its derivative. And then here we can see the way that we originally stated it, which was the derivative of the first times the second plus the first one times the derivative of the second one. So what we're going to do with integration by parts is rewind this process and rearrange some little bits. Because if you take a look at the objective slide here, the image with this really zen seesaw that's going on, our goal with integration by parts is to exchange something that is complicated for something that is far less complicated. So integration by parts happens when we're taking the antiderivative of a product. And this product is too hard to integrate, if not impossible to integrate. So what we're going to do is we're going to switch it out for something that is far less complicated, something that is integrable, something that we can take the antiderivative of. All right, so let's rewind that process of using the product rule like this. So I have that Leibniz notation, and the first step here is, let's get rid of those dx's. We got dx's on both sides of this equation, so let's multiply by dx's. Boom, they're gone. All right, now I want to undo the derivative process, so I need to take the antiderivative of both sides. So that is the next step. We're going to integrate both sides. On the left-hand side, you have the antiderivative of a derivative. Those two operations, they cancel each other out, and this is just going to give us uv, which is, of course, the product of the two functions that we're originally talking about. And then over here on the right-hand side, I'm just going to take the antiderivative of both of these pieces separately. Right, so I have uv is equal to the antiderivative of v du plus the antiderivative of u dv. So on integration by parts, what we do is we just rearrange these two things. We're going to solve this basically for the antiderivative of u dv by just subtracting the antiderivative of v du to the other side of the equation. And then what you have here, ladies and gentlemen, is integration by parts. I have the antiderivative of u dv is equal to uv minus the antiderivative of v du. So you can see that there are two antiderivatives in this integration by parts formula. The one that's on the far left-hand side is the original one that you're going to be given, one that's really hard to integrate. And we're going to switch it out for something that's far less complicated, something that is something we can take the antiderivative of. So here formally then is integration by parts. If u and v are functions of x and have continuous derivatives, then the antiderivative of u dv is equal to uv minus the antiderivative of v du. Once again, we are going to exchange the original integrand, which is impossible to integrate, and it is a product. It's a product of two things, and we're going to switch it out for the integral of v du, which hopefully should be easier, simpler to integrate. Now, of course, none of this is going to be labeled for you. You're not going to know which part is u, and you're not going to know which part is dv. Usually these things are, functions of x, or possibly t, right? So just like with u substitution, you had to get skilled at which part of it should be your u that you're going to integrate with respect to, right? All right, so I'm going to have to do the same kind of thing. Which part should be u, which part should be dv? So my suggestion here is to try to let u be the part whose derivative is simpler than u, because our first step is to take our u and take its derivative, okay? And then we're going to let the dv be the more complicated part. Okay, so this is just theory right now. So in the next video, we're going to dive into an actual example so we can see, specifically build the experience of choosing the correct thing for u and the correct thing for dv so that we can switch out the complicated integral for the less complicated one.